All right, so we'll continue on. So just a few key things about R. No, sorry. The correlation. Okay, so correlation is not affected if you add a constant or multiply a constant. Constant or multiply by a constant. The variables x and y. X or y. So if you add x, or add something to x, or add something to y, or you multiply by a constant, doesn't affect. Okay. Switching the order of x and y will also not affect correlation R. Okay. Correlation is unitless. Okay, so you look at the mean of something and it's got units, but correlation R, it's just a number between -1 and 1 that tells you the direction and strength of a relationship. Okay, and again, correlation only makes sense if the relationship is linear. It can exist even in nonlinear relationships, but the interpretations for correlation only make sense if the relationship is linear. Okay. All right, and so we'll cover this last, in this second part of class, we're going to talk about creating a regression line, okay? So we're going to talk about linear regression. So with linear regression, we are trying to model the relationship between x and y with the equation of a straight line. Okay, and so of course this only makes sense if the relationship is linear. Okay, so only works for linear relationships. Okay, so if you think back to algebra, what is the in what form is the equation of a straight line? Right, so from algebra, we'd say a straight line is y equals mx plus b. Okay, so does M represent? This is the slope, okay, and what is B? The intercept, okay, and what are X and Y? No, slope might be defined as rise over run, but what's X and what's Y? What? Yeah, these are your variables, okay? This is your X variable, and this is your Y variable, right? Okay, so in statistics, we decided to change the letters on you guys. Don't thank me. And we have, we say y hat is equal to A plus BX, okay? And so here, y hat, this is our predicted value of y. Here A is our intercept, B is our slope, and X would be our X variable.
Why predicted value and not just Y?
Yeah, that's a good question. It's because we're trying to model the relationship between X and Y. And remember, what we're looking at is we're looking at a bunch of data points. Okay, so maybe we're trying to predict how much the snake weighs if we know how long it is. Okay, and when we have an equation, what it's going to say is that, oh, your snake is 30 centimeters long. We're going to predict it weighs 160 grams or something like that. Okay, but if I were to find actual specimens of snake that were 30 centimeters long, will it necessarily weigh exactly 160 grams? And the answer is no. Okay, so in that case, the X is 30, and then the actual weight of the snake may be 165 grams. The Y would be 165. But if the model says 30, snakes of 30 centimeters long are predicted to weigh 160 grams, that's what we've got going on. We're not saying that every single snake will weigh exactly 160 grams, but we're just saying this is our prediction. And that allows to have different, have several snakes, all 30 centimeters long, that could weigh slightly different amounts. Okay, but this is what we have. We got y hat, our predicted value of y, is equal, basically the equation of a line. A slope times the x plus an intercept. But we've changed the order here. Okay, so what we want to talk about is, we have the x variable. Okay, we have several names for the x variable. The x variable can be thought of as the independent variable, the explanatory variable, or the predictor. Okay, and basically all this is saying is that in our linear regression, we are using the x to make a prediction. Okay, we're not trying to predict x, we are using x to make the prediction. Okay, so depending on how you frame the question, things can go either way. You can say, okay, if I have a snake that's 30 centimeters, what do I predict its weight to be? In that case, x would be the length, and the y would be the weight. But it could also be flipped around, and you can say, oh, here I have a snake that weighs 150 grams. Try to guess its length. And in that case, you would have them switched around. Okay? On the other hand, we have the y variable. And these have words like the dependent variable, the response variable, or the prediction or predicted variable. Okay, and then so we are trying to make predictions of y. Okay, so let me give you an example here. Looks like some of you guys are still writing, but okay. So here's an example. Okay, we're gonna look at some books. Okay, so imagine I've got a book. Okay, and we're gonna measure how wide the book is. Okay, so we're gonna measure from basically how wide is the book. So we measure the width. And we're also gonna count the number of pages. So we'll just flip to the last page in the book and we just look at the number of pages. Okay, and so what we're going to do is we're going to, based on the number of pages, we want to predict the width of the book. So which is my explanatory variable and which one is my response variable?
Number of pages, the explanatory response is the width.
Right. Okay, so the explanatory variable is the number of pages because we are using that to make our prediction. And the response is the width because this is the variable that we are predicting. Is that good with everybody else? Okay. And so we can create a prediction equation in the form of y hat is equal to a plus b x. All right. Except so our response, the width, this is our y, right? So the response is y and x is the explanatory. Okay. So what I'm going to do is instead of just using y is equal to a plus bx, I'm going to say width, and I'm going to put a little hat over it. And so this is width hat, or basically predicted width. So width hat, or basically predicted width. So what I'm predicting the width to be is equal, and then here I'm going to just throw in some numbers, 6.22 plus 0.0366 times pages, okay, where pages represents our x variable. Does that make sense? All right, and so this is our predicted width, technically in millimeters. So how wide do we predict a book that has 400 pages? Okay. How wide do we predict a book to be? If it has 400 pages. Okay, so what do we do? So I would do, I'm just going to plug in 400 where I see pages. Okay, so I'm going to have predicted width hat is equal to 6.22 plus 0.0366 times 400, because pages is now 400. So I'm going to just type that in. 6.22 plus 0.0366 times 400. I get 20.86. Okay, and so I would say, you know, I predict that a book with 400 pages will be 20.86 millimeters thick, or millimeters wide. Does that work for you guys? Okay. What if I found a book that has another 100 pages in it? So a book with 500 pages. How wide will we predict that book to be? Okay, so hang on. So I'm going to just, let me see if I can copy this over. So I'll copy this. So this is our linear regression line. Okay, and then so we said 400 pages. This became 20.86. 500 pages. Okay. Well, I want to give someone else. Does anyone else have the? Yeah. Okay. So we got. Yeah. So we'd plug in, 6.22 plus 0.0366 times 500. So basically, I can just come back here and change that to a 5, and we get 24.52. All right, what about 600 pages? Okay, 28.18. All right, so do me another favor here, and tell me how much did your prediction change between the 400-page book and the 500-page book? And how much did it change from 500 to 600 pages? Huh? So you should say, to go from here to here, we added 3.66. Yeah? And what about to go from here to here? 3.66 also, right? Okay. Are we seeing where we're getting this 3.66? Here, where's it coming from? The slope, right? This value right here, what is this called? This is called the slope. And this one's called the what? Intercept, okay. So our slope is equal to 0.0366, right? So what is the interpretation of the slope? So the interpretation of the slope is 0.0366. This is how much we expect y to change if we increase x by 1. Okay? This is how much we expect y to change if x goes up by 1. Okay, that's the generic interpretation. It's how much y we expect y to change if x goes up by 1. All right? What is our x in our example? Number of pages, okay? And what is y? Y is our predicted width, right? So what we're saying is that if we add 1 page to a book, we expect the width of the book to increase by 0.0366 millimeters. Okay, so that's a very small number. So if we increase the number of pages by 1, we expect the width of the book to increase by 0.0366 millimeters. Okay, and that makes sense because 1 page is very thin. Okay, but if you add 100 pages, how much would we expect the width to increase? 3.66. So all we're doing is we're just multiplying the slope by 100, and we're saying if I add 100 pages, I'm expecting the width to go up 3.66 millimeters. Okay? And if I were to add 1,000 pages, we would expect it to increase what? 36.6 millimeters, right? Okay. So the interpretation of the slope in this context, okay, so interpretation in this context is, how much we expect the width to increase if we add 1 page to a book. Okay, but again, because it's so small, so we would say, if we add 1 page, we expect width to increase 0.0366 millimeters. But that's kind of not very intuitive, so we can say if we add 100 pages, we expect width to increase 3.66 millimeters, and if we added 1,000 pages, 36.6 millimeters, which makes more sense. Okay, so the interpretation of the slope is how much we expect y to change if we increase x by 1. Okay, so in the context of this problem, it makes sense talking about increasing x by 1. In other cases, perhaps if you're dealing with some kind of proportion, an increase of 1 is a drastically different is a much bigger measure. So, for example, trying to think of an example. Okay, so in baseball, you have a player's batting average, okay? So batting average, the difference between a mediocre player and an excellent player is pretty small, okay? So if a player has a batting average of 0.2, that player would be considered a bad player, okay, in baseball, okay? And if a player has a batting average of 0.4, this would be an excellent player, okay? Like, I don't think there are any current players that have batting averages of 0.4, okay? And you know, 0.3 would be pretty good, okay? So the difference between a very bad player and an excellent player, it's very small. You know, the difference between 0.2 or 0.3 or 0.4, these are huge differences, okay? So if we were to try to make predictions based on batting average, and we were using batting average as our x variable, okay, then the slope would be how much we expect our predictions to change if we increased batting average by 1, okay? And so an increase of 1 in batting average would be just this ridiculously unheard of change, or even practically impossible change. And so, you know, your values for slope will be hard to interpret unless you kind of scale it down and say, like, okay, let's talk about changing our batting average by, you know, dividing it by 100. So we can say increase my batting average by 0.01 translates to this kind of change here, okay? So over here we had the problem, not a problem, but we have a slope that's really small, and it, you know, on a practical level, it doesn't really make sense until we multiply it by something like 100, okay, to get it into something that makes sense to us. On the other hand, we could have something where we're expecting x to be a quite small value, and so changes would need to be, we would have to divide them. Okay, so this is the interpretation of the slope. Let's talk about the intercept. Okay, so here our intercept is 6.22. Okay, the intercept is our prediction for y if x were equal to 0. Okay, and so essentially what we're saying is we are predicting the width of a book that has 0 pages in it to be 6.22 millimeters wide, okay? Okay, and so in the context of books, we can kind of imagine a book having 0 pages, okay? And that would be as if I tore out all of the pages and I was just left with the covers, okay? And then so this would kind of, you know, from a practical standpoint, it would be kind of the width of the covers, okay? So, you know, for books, the interpretation would be kind of like this is the width of the covers. Okay, but not all, but it doesn't always make sense to plug in the 0 for x, okay? It will not always make sense to plug in 0 for x. So for example, we could say, I don't know, we predict someone's weight based on the height, and I'm just making up numbers here. Okay, I have no idea, okay? I have no idea what this is, all right? But, so I'm just making this up, and basically what we're saying is probably not this. This is going to be completely wrong too. But anyway, here it would not make sense to plug in 0 for height, okay? Because no one can have a height of 0, okay? So the intercept will not make sense okay? Because the intercept is our prediction for y when x is 0, and we can't plug in 0 for x. Okay. But in certain cases, when it does make sense to plug in 0 for x, that's what the intercept would be. It's our prediction for y if x were 0. Okay? This is okay with you guys? All right. The slope and the intercept are determined by these formulas that have been kind of figured out by via calculus and whatnot. We don't have to worry about how things ended up this way, but the way to calculate slope. So to calculate the slope, okay, we have b, the slope, is equal to r times sy over sx. Okay, so r is the correlation. Okay, sy is the standard deviation. Of basically the y values. Okay, so imagine having your data. You have the x column and the y column. You just take the standard deviation of the y column. Sx is the standard deviation of the x values. Okay, and then to calculate intercept, I know that's how I feel with my hand at the end of every class too. Is that the intercept is a, and it's equal to y bar minus b times x bar, okay? And so y bar, in this case, is the mean of y values. X bar is the mean of the x values. And b is your slope that you found in the previous part of the previous step. So far, so good? Okay. Okay, there's this concept of a residual. Okay, the residual is the difference between our prediction and the actual value. Or I should say between the actual value and our prediction. So this is a topic that's not covered in the textbook for whatever reason, but I think it's still very important. And so let's say we're using our prediction between this is our regression line for width based on pages, right? So this is our prediction equation. Okay, and so let's say I have a book with 400 pages in it, or we'll say with 600 pages in it, and I measure the width it is 31 millimeters thick, 31 millimeters wide. Okay, so my actual data point is x is equal to 600 and y is equal to 31. Okay, based on our equation, our regression line, okay, when x is equal to 600, we predict y. We predict y is, what do we predict y? We say y hat is equal, and then I do 6.22 plus 0.0366 times 600, and I get 28.18. Right, so I plug this in and I get 28.18. 6.22 plus 0.0366 times 600, I get, this is what I'm predicting to be, okay? So my residual is the difference between the actual value and our prediction, okay? So we can say the residual is equal to y minus y hat, or actual minus predicted. So here, in our case, the actual value is 31, so my residual is equal to 31 minus the predicted value of 28.18. So I do 31 minus 28.18, and I get 2.82. So my residual is 2.82 millimeters. Okay, and so this is one way to measure, how good does our model perform. If we have actual data values, we can kind of measure how much of a difference is there between the actual data values and the predictions we're making for it. Was there a question over there? 28.818. So so I'm basically just plugging in 600 in for pages, okay? Because I'm saying here I have x equal to 600, so I'm just going to plug in 600 here, okay? So I do 6.22 plus 0.0366 times 600, and when you punch that into your calculator, you get 28.18, okay? So that's what I'm predicting the book's width to be if the book has 600 pages in it, okay? And then so if you actually have a book that has 600 pages, you can see, well, how good is my prediction compared to the reality, okay? And you just say, okay, well, let's just take the difference between the actual value and what I predicted. And so if this number is really tiny, that's a good prediction. And if the number is huge, then it's not so good of a prediction, okay? So is 2.82 a big number, small number? I guess that's up to you. How much does it really matter? Maybe it doesn't really matter. Okay, I don't know. Maybe you're like a bookshelf designer and you want to say, like, my bookshelves can hold 40,000 pages, so I'm designing it to be this, whatever. I can't imagine a scenario where this is critically important, but there could be something, right? Maybe you're setting a budget and you're trying to predict how much money you should allocate, and you're going to try to predict. You say, like, oh, we're going to buy this many slices of pizza for the year, and you can create a regression equation based on that or something, okay? All right, so a few things to watch out for, okay? So just a few warnings. Okay, so do not do linear regression if the shape is not linear. if your data looks like, okay, don't try to fit a straight line. Okay, this is bad. Okay. Do not make predictions in areas where you have not collected data. Okay, and this is probably a common mistake that people use regression incorrectly for. Okay, this is often called extrapolation. Okay, so here's a silly example. Okay, let's say you have a child. You measure how tall this child is at, every 6 months or so. Okay, so maybe you've done this since this child was 3 years old. So you're measuring the height and the age. Okay, so starting at 3 years old, and then you go to 4, 5. So every 6 months you measure how tall this kid is, and it looks like this. All right, and so maybe you're now at age 13. Okay, and you're like, wow, this kid has grown about an inch every single year or whatever. Okay, all right. Would it make sense to then say, oh, okay, well, look at this. It fits a straight line. That's great. Let's see how tall my child will be when he's 55 years old. No, okay. This doesn't work, right? So, now we're trying to make a prediction at 55 years. What's going to happen? Is your kid going to be the tallest person in the world? No, okay. Because the reality is that, yeah, sure, kids grow a lot their first, maybe 20 years of life or whatever, okay, 18, but around age 20 or something, things, 18, 20, they stops, okay? Some people stop growing when they're like 14, okay? Everyone's different. I guess some people grow until they're like 21, but that's relatively rare. Okay, so we can't do this, but people do this all the time, especially in politics and in news. They're like, for the past 20 years we've seen this trend, so by the year 2050 or 2100, this is what the world's going to look like. And the truth is nobody knows what the future is going to look like. Okay, yes.
You say do not make predictions in areas where you do not collect data, but isn't that why we make predictions in a sense? Because
I wouldn't say so. I wouldn't say that's why we're not always trying to make predictions about the future or something, okay? So it could be, so for this we could say maybe you missed measuring the kid's height on his 7th birthday, okay? Here you can use this to fill it in, okay? Or you can say how let's say you've got a whole bunch of data, right? What is, let's say, I don't know, going back to the snakes, okay, you want to know how much is a snake supposed to weigh if it's, 25 centimeters long, okay? I think that's a reasonable question to ask, and maybe you have other specimens that are already 25 centimeters long, but I think the regression equation will give you kind of a better idea of what the prediction should be, okay? So yeah, we don't do regression just to make predictions in where we have no idea what's going to happen, okay?
you have to have some sort of idea.
Yeah, you need to have some data collected in that general vicinity to get an idea. Yeah, another question.
Does that apply to the linear spectrum slope as well?
Well, I mean, this is just linear regression as a concept, as a whole, okay? We can't use linear regression to make predictions for the future, okay? Really. I guess this is just to say you can't predict the future, no matter how hard you try, all right? We can try to get some guesses, okay? And if the future is only like a couple days away, sure, we can do it, okay? But trying to predict the future, if, you know, and we're talking about, like even just like the past few months in politics, right? Like we can probably predict what's gonna happen maybe 1 week from today, all right? Based on all of the polling data and all of this stuff, we can kind of get an idea here. But what's going to happen in November, we have no idea, right? And then if you ask, you know, what would the political landscape look like? If you asked us that question 6 months ago, everybody's answers would have been like way off, right? Because 6 months ago, nobody really saw any of this coming, right? So, yeah.
So what about with like climate change though? Scientists always predicting.
Yeah, you know, I mean, this is, so there's a lot of data and evidence for things that have happened in the past, and I think there's a lot of data and evidence there. But as far as what's going to happen in the future, nobody really knows. Okay, and we can kind of get an idea of what might happen in the next year, 2 years, or something like that. Okay, but what's really going to happen 50 years from now or 100 years from now, nobody really knows. Okay, I think a lot of the debate regarding climate change is the data we have evidence of man-made created climate change, yes or no? And that's mostly in the past. And I think that's a legitimate question, and I think there's a lot of data supporting certain positions for that. But in terms of what's going to happen in the future, no one really knows. Okay. All right, let me keep talking here. So I said, don't make predictions here. Okay, also beware of outliers. Okay, so outliers can really affect the way things appear. Okay, so for example, let's say this is your data here. Okay. Okay, if this was it, we would say what? No trend, right? Okay, now let's say we do have some kind of outlier. Okay, and okay, and then suddenly, you know, we have a data point way out here. Okay, and then so suddenly the trend, if we were to fit some kind of regression line, it would suddenly try to accommodate this thing, okay? So over here we would say, oh yeah, no trend, okay? But now suddenly, because of this outlier, makes it appear like there is a negative trend. Okay. So it's kind of like, you know, basing the entire trend based on just one kind of very unusual data point, okay? And that's probably not a wise thing to do. Okay, so we could say, you know, it would just be like, you know, saying like, oh, what effect does outer space have on, I don't know, dogs or something, okay? And then you throw one dog into outer space and you go, oh, well, okay. Now we're gonna write an entire novel and story about the effect of outer space on dogs. It's probably not a good idea. You'd probably want to collect more data than just using one data point there, okay? So beware of outliers, because that can create.
Points are considered when it's not an outlier anymore. When if there's like 2 or 3 of those points, so it's not an outlier.
Okay. Let's try this. All right. So if you have something, all right. So let's say you have like this. Oh, sure. Then it's reasonable to say like, okay, we have multiple data points indicating that as you get out into this land of extreme, there's a negative trend. That's fine, okay? But you got one data point out here. That's not a good data, because who knows? Maybe someone else collects data points. Let's say this is, I don't know, based on, I don't know, how much money you have or something, okay? So you interview, like, I don't know, this is like, how many sodas do you drink, okay? And this is like, how much money do you have, right? So probably how much money you have and how much soda you drink, probably there's not too much relationship. Well, maybe there is, but okay. And then so you ask someone who has $1 billion, how much soda do you drink? And this guy says, oh, I don't drink any soda. So then would it be fair to say, like, oh, more money says you don't drink more? Because maybe you ask another person who has $1 billion and that person drinks a ton of soda or something, okay? Then you realize, okay, there's no real relationship here. But if you just have one person out here, they might mislead you. Okay, and then last thing will be correlation is not the same as causation, okay? So just because two things happen together does not mean one causes the other. Okay. Correlation could give us an indication of things that we should investigate for causes, but it does not necessarily mean one causes the other, okay? Correlation can help us, can aid in an investigation, can aid in an investigation for causes. Okay, but is not proof of cause in of itself. Okay, so if we were to look at number of appliances in a house, okay, appliances, things like TV and washer and blender, etc. And then we look at academic performance of the kids, right? Okay. Overall, we would see some kind of positive trend. Okay, we would see a positive correlation. Maybe not super strong, okay, but we would see some kind of positive correlation. We would see that houses with lots of appliances generally have students that perform academically well. Houses with very few appliances generally will have students that perform poorly. And there is actual studies, actual data that kind of back up this thing. So does this mean that to increase academic performance, we should just give blenders and toasters to families? And that will help? No, okay, that doesn't work, right? What's going on? Okay, so I mean, even that, right? So we might say, oh, okay, well, there's different incomes and different economic things going on, but even that doesn't really answer why there's a difference between academic performance between families with great income and families with low income. Even that doesn't answer. I mean, I think people start to have have reason, think, but if it was as easy as just a matter of income, then the answer would just be to increase income across the board. But that in of itself is not the answer, and I think the answer is much more complicated, and there's a lot of things at play, of which economics and income is a factor, but is not the only factor. Okay, and so correlation, these things are correlated, and it's very interesting, but they in of themselves are not the causes. Okay, I'm going to actually take attendance, a live attendance here, and then and this will count as your in your attendance grade here. So I'm going to stop the video here, and then I'll just go down the roll, and we'll take actual attendance.